Hello, this is Deborah Barrett with the Cincinnati State Physics Department presenting the third in a series of videos on momentum. This will be a sample solution of a problem from Chapter 7 of Giancoli's Physics. We're going to do Chapter 7, Problem 4, which is on page 188. You recall that we have a set of steps we go through for problem solving that help us make our way through. The first step is to read the problem. So on page 188, Chapter 7, Problem 4, a child in a boat throws a 6.40 kilogram package out horizontally with a speed of 10.0 meter per second. Calculate the velocity of the boat immediately after, assuming it was initially at rest. The mass of the child is 26.0 kilogram, and that of the boat is 45.0 kilograms. Ignore water resistance. I'd like to suggest you take a moment and open up your text to page 188 to read the problem for yourself. I'm going to suggest you pause the recording for a moment while you do that. Now that you've read the problem, our next move is to imagine the situation. This is helped by the fact that they have a little picture in the book showing the kid throwing the package. I have to tell you, that's a pretty hefty package. I always think it must be the fruitcake. You know how Aunt Matilda sends fruitcake at Christmas time and not everybody likes fruitcake? I think the child is throwing the fruitcake overboard. Our next move is to make our sketch for labeling. So I'm going to show you the sketch that I have for us to help with this situation. So here's my sketch. Extremely artistic, as you can see. When we are going to have multiple objects at multiple times to deal with, and that's kind of complicated. So I often think it's a good idea to make separate sketches for those multiple times. So as you can see, I've got a time 1 sketch at the top of the page showing the child holding the package in the boat. And on the bottom of the page, I have another sketch for time 2 showing the child without the package and the package flying along. So this is my sketch. Our next step, as you know, is to equate, which is to label the sketch with tiny information equations. They tell us the mass of the package is 6.4 kilograms. So I'm going to subscript mass with a P to stand for mass of the package, 6.4 kilograms, and I've labeled that on the package where it's flying along. They also have told us that that the package is moving with a speed of 10 meters per second, so I'm going to label that also. I am going to use the subscript 2 to represent time 2, so my label for the velocity of the package as it flies through the air is V sub package 2 equals 10 meter per second. Next, I will label the information about the mass of the child and the mass of the boat. And since at time 2 the child is in the boat, I think I'm just going to combine those two together. The mass of the child is 26 kilograms. The mass of the boat is 41 kilograms. So that's a total of 71 kilograms for the mass of the child and the boat together. And that's how I'll label that. So there we have the mass of the child in the boat at time 2, marked as 71 kilograms. Now, at time 1, the child and the boat and the package are all sharing the same motion, so it should be safe to list them to have a joint velocity of 0 and to show them having a joint mass of 77.4 kilograms. So that's what I'm going to do. So here we've got the mass of the child in the boat with the package at time 1, labeled as 77.4 kilograms, and the velocity of the child in the boat with the package at time 1, labeled as 0. The only other thing I think we need to label is the unknown that they've asked us to find, which is the velocity of the boat after the package is thrown. So there's our unknown, the velocity of the child in the boat at time 2. Notice that based on what happens when you throw something out of a boat, I've drawn the boat off to the left of the package and off to the left of where it was at the start of the problem. I anticipate that the boat is going to move to the left if the package goes to the right. So I'll just add a little vector arrow to show that that's which way it's going. So now we've finished reading, imagining, sketching, and equating. It's time to choose a relationship that ties these different things together. Let's see, what we have are masses and velocities, and we know that the weight of the boat would be balanced out by the support force that the water applies to the boat. So as long as we're ignoring water resistance, then there are no outside forces on the child with the boat and the package, other than the slight unbalanced force of gravity on the package itself. That's a small enough force that we should be able to neglect it. So we've got all the things we need to find momentum, and in fact, momentum should be conserved in this kind of a situation. So let's put down the momentum equation, the conservation of momentum equation. So our equation is conservation of momentum, that the sum of all the momenta at time 1 must be equal to the sum of all the momenta at time 2 for our isolated system, keeping in mind that momentum equals mass times velocity. So next, let's fill in the conservation of momentum equation. We have, for time 1, we have the mass of the child in the boat with the package multiplied by a velocity of 0. So the left-hand side of the equation, 77.4 kilograms of mass at time 1, multiplied by 0 velocity at time 1. Now for the right-hand side of the equation, at time 2, we'll have to have two separate terms. We can combine objects in a single term if they're sharing the same motion. So we'll be able to do the child and the boat together for time 2. But the package has to be handled separately. So I'll next put in the mass of the package times its velocity. So there we have our 6.4 kilograms times 10 meters per second for the package. And then to incorporate the child in the boat, we'll have 71 kilograms times the unknown velocity. So now we've got our 71 kilograms times V2. I decided that since we only have one unknown velocity, I wasn't going to bother calling it V child in the boat 2. I'm just saying velocity at time 2. Now all we have to do is finish up the algebra and we will have our answer. We finish up with the velocity for the child in the boat at the moment immediately after the package is thrown being a negative 0.901 meter per second. That matches our expectation that the boat would jerk backwards if the package were thrown forwards, that negative sign, giving us the directionality that we were expecting. This completes the solution of problem 4 from chapter 7. There will be more videos coming pretty soon. Thank you for looking at your momentum.